Now we're going to talk about projections. There's a lot of material in this section, and it's not so easy, so I suggest you set aside a little bit of extra time to learn it. So the question is, we have a vector and a line, and we'd like to compute the projection of the vector on that line. That is to say, the orthogonal projection. So, or another way to say it is, it's the closest point to the line. Clearly something that's going to play a role here is this angle theta and its cosine. So that's where the cosines come into the picture. So we're going to first talk a little while about cosines and some formulas and results about the dot product, and then we'll return to the subject of projections. So there are two basic laws relating some vector stuff and cosines. And to get the idea, let's start with the fact that, remember, we've been talking about the dot product, v dot w. I'll also sometimes write that as v transpose w, or maybe even the inner product of v and w. And remember that v dot w is 0 if and only if the vectors are orthogonal. They make a right angle with each other. And in other words, the dot product is 0 if and only if the cosine of the angle between them is 0. Because if you have two vectors and they have an angle between them, remember that the way you tell if an angle is a right angle is if and only if its cosine is 0. So orthogonality is given by the cosine being 0. Okay, so here's the first law relating this business. Suppose you have two vectors v and w with an angle between them. Take their dot product. Well, the law says that the dot product has the following formula. It's the length of v times the length of w times the cosine of the angle between the two vectors. Well, that's kind of interesting. So another way to write this is a formula for the cosine, which is to say the cosine can be computed as v dot w over the length of v times the length of w. The nice thing about this formula is on the right-hand side, it's just some basic linear algebra stuff, and that's telling you how to compute the cosine. So let's illustrate why this is true. Let's consider the case where both v and w have length 1, so they lie on the circle. And we may as well rotate them so that the first vector is over here at 1, 0. And then the second vector will be at some point cosine theta, sine theta. And where theta is the angle between those two vectors. And if you compute the dot product, you get 1, 0 dot cosine theta, sine theta. And that's cosine theta. So that's basically why this is true. Now, there's a little more to say. There's the fact that it scales the way it does if v and w aren't unit vectors is not hard to see. But anyway, that's the basic idea. So let's look at a couple of examples. Well, let's look at v dot v. The formula says that v dot v is the length of v times the length of v times the cosine of the angle between v and itself, which is to say 0. And the cosine of 0 is 1, so this says that v dot v is equal to the length of v squared, and that's something we know. Okay, there's another law which is closely related called the Law of Cosines. And you all remember, of course, that the Pythagorean Theorem says when you have a right triangle, a squared plus b squared is equal to c squared. Well, what if it's not a right angle? So we still have a, b, and c, but now we have some angle, which I'll label theta. What's the formula for the length of c in this triangle? And that's exactly the Law of Cosines. And the Law of Cosines says that c squared is a squared plus b squared minus 2ab cosine theta. So I like to think of this as being the Pythagorean theorem, a squared plus b squared, minus a correction term, 2ab cosine theta, which is 0 if theta is a 90-degree angle. So we're thinking in terms of vectors, so let's look at the vector version of this. Suppose you have two vectors v and w. Well, you complete a triangle, and the third leg of the triangle is the vector w minus v. And if we focus on this angle theta between v and w, the law becomes the length of the opposite side, w minus v squared, is the length of the two adjacent sides, v squared plus w squared, minus 2 length of v, length of w, times cosine of theta. So that's a totally equivalent version of the law of cosines. And just to help you go back and forth, this w minus v is the c, and the length of v and w are the a and b. Okay, I'd actually like to prove the law of cosines. I know you guys aren't big fans of proofs, but I want to show you that there's really no magic here. It's just an application of the Pythagorean Theorem. So we have this triangle ABC. We're trying to compute C. And what we do is we divide this triangle up by dropping a perpendicular here down to the side labeled B. And now we use the Pythagorean theorem in these two triangles, the cosines in these two triangles. The length of this side is a cosine theta, so the length of this side is b minus that, and the length of this vertical leg here is a sine theta. Well, now look at this triangle here on the left. We know two sides of it, and by the Pythagorean theorem we can compute the third. C squared is equal to b minus a cosine theta squared plus a sine theta squared. And now you just have to work out the right-hand side and see what happens. So let's do that. When you square the first term, you get b squared plus a squared cosine squared, plus the mixed term, or minus 2ab cosine theta. And the other term gives you an a squared sine squared theta. And now the a squared sine squared and the b squared, a squared cosine squared, add up to a squared. So you get b squared plus a squared minus 2ab cosine theta, and you're done. Okay, now let's go back and look at the first law. And I'm going to show you how to derive the first law from the law of cosines. So remember, the first law is this, that v dot w is the length of v times the length of w times cosine of theta. So why is that true? I'm going to use the law of cosines to see why. So let's draw this third leg here. And what I know by the law of cosines is that the length of that leg squared is equal to the length of v squared plus the length of w squared minus 2 length of v, length of w, cosine theta. And, well, we're just going to basically write this out and cancel some terms to get what we want. So w minus v squared, that length squared, is w minus v dot itself. And that's supposed to equal v dot v plus w dot w minus 2. And I'm just going to leave the length of v and length of w cosine theta. And now on the left-hand side, we get w dot w minus 2v dot w plus v dot v. And the right-hand side I'm not going to touch. And now you just cancel the w dot w on both sides. And also the v dot v. And also the minus 2's, and I conclude exactly what I want. v dot w is equal to length of v, length of w, cosine theta. So these two laws are really very, very closely related to each other. Okay, now let's go back and look at projections. So I've got my line L, and to describe my line L, let's say we have a vector W, and we take L to be the span of W, all the multiples of W. And then I have some other vector V, and as I said, I'd like to take the orthogonal projection, make this a right angle, and compute the projection onto the line. By the way, this is a very important operation. We're going to be using this in doing least squares and other things later on. In any event, so clearly the projection of V onto this line it's some multiple of w. It's on the line, so it's some multiple of w for some scalar c. That's not supposed to be a vector. And all we need to do is find this c. Well, how do we tell? The point is that this vector that I'm looking for, c times w, is the red one here, and this other vector is therefore v minus that. And the condition is that they're supposed to be perpendicular. So CW is supposed to be perpendicular to V minus CW. And that clearly determines C. Well, let's see what it gives. So you compute the dot product of these two vectors, and it's supposed to be 0. And so what we see is CW dot V minus C squared W dot W is supposed to be 0. So that says that CWV dot V is equal to C squared W dot W, and we cancel one of the C's. And we conclude that C had better equal W dot V over W dot W. And that is to say that the vector itself is this scalar V dot W over W dot W times the vector W. Okay, so let's summarize that. The theorem is the following. We have a vector, and we have a line, which is the multiples of a vector w. And to compute the projection of the vector on the line, that is to say the line through w, the formula is the projection of v on the line is equal to the following vector. It's the scalar v times w over w dot w times the vector w. It's this scalar times the vector w. Okay, for the last thing I want to talk about is how we write down projection as a matrix. So again, the picture is we have a line through a vector w, and we're projecting v onto the line. And so I want to think of this projection operator as a map from Rn to Rn. P of v, P is a map from Rn to Rn, and it's, if you think about it, it's clearly linear, so it has a matrix. What's the matrix of this operation? Well, I have a formula for P of v. It's w dot v over w dot w times w. And now it's convenient to write our vectors as column vectors and use the transpose business instead of the dot product. V dot w is v transpose w. So we get w transpose v over w transpose w. That's a scalar times the vector w. And now we do this really clever thing, which is we put the w on the other side, which seems kind of trivial. Well, it is kind of trivial when we write it this way. But now we can pull the v out on the right and write this as w times w transpose over w transpose times w, all of this times v. Okay, there's a formula. Now, it's kind of strange looking. We need to stare at it for a minute. I'm claiming this thing on the left is an n by n matrix. How can that be? Well, the denominator w transpose w is a scalar. But the numerator, it's in the other order. I'm literally multiplying these two vectors, and I'm multiplying it's actually a column vector, that's what w is, times a row vector. And when you do that, you don't get a scalar, but you get the opposite. You get an n by n matrix. So that's what this thing is. And so let's state the theorem now. The matrix of a projection, which is to say you want to project a vector v onto a line through given matrix w, given vector w, the matrix of this operation is w transpose over w transpose w. And I'm also going to state that this matrix is symmetric, and it satisfies the property that when you square it, you get itself again. M squared is equal to M. Well, these second two assertions, it's symmetric is clear from the formula, this WW transpose thing. We'll see in an example. And the fact that M squared is equal to M is because if you project a vector twice, nothing extra happens. Once you've projected it once, projecting it again doesn't do anything. There's V. You project it to get its projection, and then the projection of the projection is itself. So that's why M squared is equal to M. Okay, it's time for an example. Suppose W is the vector 2, 1, and let's compute the matrix of projection onto this line. So, as I said, the matrix is computed like this, where W, it's important to remember, is now a column vector 2, 1. So what you get is the column vector 2, 1 times the row vector 2, 1 over the row vector 2, 1 times the column vector 2, 1. The numerator becomes 2, 2, 2, 1. And the denominator is 5. So we're getting 1/5 times this matrix. And notice the matrix is symmetric. You can also bring the 1/5 in if you want. That's the matrix of this projection. So let's, for example, suppose V was the vector 2, 6. What is its projection? Well, you just apply this matrix to it, and you get 1/5 times, let's see, 8 plus 12 is 20, and 4 plus 6 is 10, and you're getting the vector 4, 2, which is indeed on the line. It's 2 times the vector 2, 1. The vector that I started with, 2, 6, is kind of hard to draw in the picture. So, and let's compute the projection again. If you project the vector 4, 2, you get this matrix operation, which is to say 1/5, 16 plus 4 is 20, and 8 plus 2 is 10. You're getting 4, 2. Aha! When you project 4, 2, you get itself. Good. All right, that's a lot for today, and I'll call it quits.